Hi, hello, welcome. This is Discrete Mathematics, and today we're talking about arguments and rules of inference. Let's start off with a couple of arguments. Here are two statements. The first one, if John is running, then he is exercising. Second statement, John is running. If we know those two statements to be true, what can we conclude? John is running, then he is exercising, and we know that he is running. Therefore, I'm going to use these three dots in a little triangle shape to denote therefore. Kind of a long word, save ourselves some time with the three dots. Therefore, he is exercising. We could write these statements in symbolic form. Let's say John is running, that's P. He is exercising, that's Q. So P implies Q. That's our first statement. John is running, that's P. Therefore, he's exercising, Q. So here is one argument. Our argument is a series of written propositions that have a conclusion. Let's look at the next one. The bug is in either Module 17 or Module 81. The bug is a numerical error. Module 81 has no numerical error. So we know there's a bug. We know it's in one of two modules, but we know that one of the modules doesn't have a numerical error, and we know that it's a numerical error. So it must be in the other module. So we can conclude that the bug is in Module 81. And we can write, in 17. And we can write this one in symbolic form as well. The bug being in Module 17, let's say that's P. Module 81 is Q, so P or Q is in one of those two modules. The bug is a numerical error. Let's call that R. That's another statement. The Module 81 has no numerical error. So if the bug was in Module 81, then it's not going to be a numerical error. So Q implies it's not a numerical error. Therefore, the bug is in Module 17, P. An argument is a series of written propositions. These propositions are called hypotheses. So up here we can have hypotheses. So there can be n of them. So far we've seen an argument with two hypotheses and an argument with three hypotheses. We'll take a look at different lengths of arguments. But all of these arguments have a line and then this thing, and that thing is the conclusion. P is called the conclusion. And it's usually accompanied by those three little dots that signify therefore. So when we are considering our arguments, we do not have to try to adjudicate the truthfulness of each hypothesis. We are just supposed to assume all these hypotheses are true. Does the conclusion follow from that? If they are all true, does the conclusion follow? That's what we're trying to figure out. And if it is true, the truth of the hypotheses mandates the truth of that conclusion, then the argument is considered valid. If it does not follow, if the conclusion does not follow from all those hypotheses, then the argument is considered to be invalid, or sometimes we call it a fallacy because it is false. We do not, again, like I said, you do not have to determine whether or not each hypothesis is objectively true. We're just assuming they're all true. Does that mean the conclusion is also true? How we're going to make that determination is using these rules of inference. There are quite a few of them here. We're going to go through them and give them all names. That way, when we see arguments in the next few examples, we'll have a way to name why we are concluding what we are concluding. It's because we're going to use these rules. The first argument we have is P implies Q, P, therefore Q. This is the argument we used up with John. If you remember the truth table for P implies Q, the only way that P implies Q can be false is if P is true and Q is false. And here we know that P is true, and we know that P implies Q is true, so Q has to also be true. This argument is, this rule of inference is called modus ponens. This is Latin. This is Latin for mode that affirms. Mode that affirms. So many of these rules of inference have names that are interesting, so we'll go through all those. Next rule, P implies Q, not Q, therefore not P. This rule is called modus tollens. This rule is kind of uses the contrapositive. So P implies Q is the same thing as not Q implies not P. So there, now we have not Q, so therefore we have not P. It's kind of like a combination of the contrapositive and modus ponens. And since we want to use this argument so much, it has its own name, modus tollens. Next rule, P, therefore, P or Q. This one's called addition. What we know about or statements is at least one of those things has to be true. So if we know that P is true, you can or it with anything else. It doesn't matter whether that thing's true or false because we already have the at least one true thing in P. Next up, P and Q, therefore P. This one is called simplification. P and Q requires that both P is true and Q is true. So if you know P and Q is true, then you know that P is true. You also actually know that Q is true. So that's another version of this simplification, is that Q can also be true because this or is commutative. So this is the same as Q or P, or sorry, Q and P. And then you would have, therefore, Q. Put that one over here. That's simplification. Next one, P is true, Q is true. Therefore, P and Q, this one's called conjunction. So P and Q requires that both P and Q be true, and there we have both P and Q true. So we can add them together. Next one, P implies Q, Q implies R, therefore P implies R. The thing to look for here is that these two things are the same. This is sort of like a transitive property. P implies Q, Q implies R, therefore P implies R. It's not called that though, it has its own name, and that name is hypothetical syllogism. Say that 3 times fast. Hypothetical syllogism. It would be easier if it's called transitive something, but it's not. I'm sorry, I didn't name these. Next one, P or Q, not P, therefore Q. This is like saying you can have, for breakfast, you can have either pancakes or waffles. And then you say, well, I don't want pancakes. Well, then you're going to get waffles. This one's called disjunctive syllogism. It's pancakes or waffles. Throw in some crepes in there. I do love some crepes. P implies Q, therefore not P implies not Q. We kind of already saw this one over right directly across in modus tollens. This is the contrapositive. So we call it the contrapositive equivalence. Next one, not P, therefore P. This is called the not equivalence. Some of these names make more sense than others. This one obviously makes a lot of sense. We had a version of this with sets. We had A complement complement is the same thing as A. So this is not P is the same as P. Last two are basically the same, just one opposite of the other, and that's biconditional. P if and only if Q, therefore P implies Q, and also Q implies P. It goes both ways. So you can kind of break up this arrow separately. So these are both definition of biconditional. So keep this chart handy because we're going to use this chart when we're doing to check to see if our future arguments are valid or not. We're going to be using some of these rules. Okay, there are 2 ways to prove the validity of an argument. One of them is to use those rules that we just talked about. That's often the easier way. Another way is you can look at a truth table and look at all the rows where the hypotheses are true, and then check to see if the conclusion is true. And if you can find a row where all your hypotheses are true, but your conclusion is false, then you know the argument is invalid. But if they're all true, everything's true, then the argument is valid. We'll take a look at both ways. You can determine which way you like better. Here in example 1a, I want to rewrite these arguments in symbolic form and determine if they're valid. P is I study hard, Q is I get A's, and R is I get rich. A, we have if I study hard, then I get A's. I study hard, therefore I get A's. So if I study hard, then I get A's, is P implies Q. I study hard is P, therefore I get A's is Q. So looking back at my rules of inference, does this match any of those rules? And it looks like it does. It looks exactly like this argument. So this one is modus ponens. So this one is valid via modus ponens. So that is using arguments. I did not have to use multiple arguments. We'll see examples. The next one, I think, where we'll have to use multiple arguments to get there. But this one, I was able to do it in one shot. This is directly modus ponens. Let's take a look at the truth table. So here, I'm going to draw my table. I'm going to have P and Q. That's not a very good Q. And then I'm going to have my hypotheses. That's P implies Q and P. And then I'm going to have my conclusion, which is Q. So what I'm looking for is I want all of these to be true and this one to also be true. That's what it means to be a valid argument. So we're going to look at every single combination. True, 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 false. Whoopsie. Sorry, this is false. False, false, true, false. All right. So if P and Q are both true, P implies Q is also true, and then P is true. I'm repeating it here because it's one of my hypotheses. So this is my whole hypothesis area that I want to look out for. So that's why I wrote P again over here. And I wrote Q over here because it's my conclusion. Let's see. P implies Q is false, and P is true. And Q, let's see. P implies Q is true, and P is false. P implies Q is true, but P is false. And now I'm looking at all of my values for Q, true, false, true, false. So now I'm interested in the rows where all of my hypotheses are true. And that's why I have them separated in this middle box. So they're only all true in this row. So I look at my conclusion, and it's also true. So this is a way to tell that this argument is a valid argument, because the only row where all of my hypotheses are true, my conclusion is also true. So this is valid. Okay, let's look at the next one. If I study hard, then I get A's. If I don't get rich, then I don't get A's. Therefore, I get rich. Is this a valid argument? Let's take a look. If I study hard is P, then I get A's. That's Q. If I don't get rich, that's not R. Then I don't get A's. That's not Q. Therefore, I get rich, R. So what can we do with this? Let's see. Well, I think I can turn the second row. So I'm going to start to label my rows, row 1 and row 2. So row 3 down here, I'm going to say, I'll put it over here to make sure I have enough room. For row number 3, I'm going to say that Q implies R. And that's from row 2. That's and I'm using the contrapositive equivalence. So now I can say in row 4, if I know that P implies Q and Q implies R, I know that P implies R. That's from rows 1 and 3 together with that's the transitive one. Hypothetical syllogism. Okay, so now let's see. This is actually different than R. I haven't really proved anything about R. I've just proved that P implies R. So this isn't R. And I'm trying to think about how can I isolate and just get R. And I'm not sure that I can. So I'm thinking this one might be invalid. So I'm going to put a little invalid over here with a question mark. And let's look at the truth table and see if we can find any rows where this one is invalid. So I've got P, Q, and R. And then my hypotheses are P implies Q, and not R implies not Q. and then I've got R over here. So what I want to look at is any rows where these are true and this one is false. So let's see, I want P implies Q to be true. So let's have P and Q both be true. Then this is true. Let's have R be false. Well, I guess, let's see. Is it possible to have R be false here? Maybe not. Maybe that's not true. Maybe that's not possible. Well, let's just do true, true, true. All trues. So then not R implies not P. That's going to be true. But then R is true. So that one doesn't work. What about... So I could do the whole table and just plug the whole thing out. But I think I'm going to skip down to, what if I did false, false, false? We've done a lot of practice with truth tables, so I don't think I'm going to do the whole table. But what if I skipped down to the false, false, false? Then P implies Q is true. It's vacuously true, we call that, because if the first one, the if statement is false, then the whole thing is true, just because it is. That's how it works. Not R, which is true, implies not Q, which is true. So this is also true, but R is false. So here we see the row where we get both of my hypotheses are true, but my conclusion is false. So I don't necessarily, if I'm trying to prove something is invalid, I don't necessarily need the entire table. I just need the one row, or maybe there's multiple rows, where, but I don't need to show multiple rows. I only need to show one row where all my hypotheses are true and the conclusion is false. So this means that this argument is invalid. Okay. And when you're trying to show an argument is invalid, you do have to find this row. You can't just do what I did over here and said, I can't figure it out from the rules because maybe you just missed one of the rules. Finding the line from the truth table is the definitive way that you show an argument is invalid. Okay, next up, C. If I study hard, then I get A's. If I don't get rich, then I don't get A's. Therefore, if I study hard, then I get rich. If I study hard, then I get A's. P implies Q. If I don't get rich, then I don't get A's. So not R implies not Q. Therefore, if I study hard, P, then I get rich, R. So how can we prove this argument? This one is going to be true. If you remember the last one, you'll maybe notice that I'm doing similar things. So I'm going to call those statements 1 and 2. Now from statement 3, I'm going to say, well, Q implies R, and that is from line number 2. And the rule that I'm using is the contrapositive equivalence. Then I'm going to say, well, P implies Q and Q implies R, therefore P implies R. And that is from statements 1 and 3. That's that transitive one, hypothetical syllogism. And that's it. That's what I was trying to prove. Therefore, P implies R. So this argument is valid. And this is the way to show that. If you wanted to use a truth table to show an argument was valid, you do have to show the whole table, all the rows. So for this one, you would have to, if I go back up, you would have had to show this whole table, not just 2 rows. There are 8 rows in this table. You would have to show all 8 rows. Okay, D. If I study hard, then I get A's. If I don't get rich, then I don't get A's. I study hard. Therefore, I get rich. Let's see. If I study hard, then I get A's. P implies Q. If I don't get rich, then I don't get A's. P implies not Q. I study hard. P. Therefore, I get rich. R. So 1, 2, and 3. So I'm trying to prove something about R. Let's see. Well, I think sometimes I don't exactly know where I'm going to go, but I see things in my argument that I can go with and see if that helps me along the way. So one thing I'm seeing is rows 1 and rows 3 look like modus ponens. P implies Q, and I know P, so therefore I know that Q is true. That's from rows 1 and 3, and that's via modus ponens. And then let's see, not R implies not Q. And I know something about Q, so let me scroll back up here and see if this will help me at all. Oh, that actually looks a lot like modus ponens. So I'm going to come back down here. And I'm going to say in step number 5, I know R, and that's from 2 and 4 with modus tollens. So this argument is also valid. All right, ready to move on to example 2. What rule of inference is being used? Here I have in part A, baseball is popular. Therefore, baseball is popular or soccer is popular. I'm going to write out with symbols. I'm going to say baseball is popular, that's P. Baseball is popular or soccer is popular is Q. So I have P, therefore, P or Q. This looks like a rule. This one looks like, let me scroll up a little bit. P, therefore P or Q. Which rule was that? That is addition. P, therefore P or Q. So this rule is called addition. Next up, Tom is a tall man, or the sky is blue. So P or Q. The sky is not blue. Not Q. Therefore, Tom is tall. P. P or Q. Not Q. Therefore, P. This looks like the pancake or waffles one. Pancakes or waffles, but this case we're not having waffles, so therefore we're having pancakes. Which one was that one? That one was this one over here. Disjunctive syllogism. This time we had the version where it's P or Q. We had not Q, therefore P. Remember, this or is also commutative, so we can write it this way, and it's the same. So this is disjunctive syllogism. Part C, the weather is cold outside and it is really warm out. Therefore, it is really warm out. This is a great one that's an example of the actual objective truthfulness of the hypotheses is not something that we're considering. We're just assuming that these are all true. The weather is cold outside, that's going to be P. It's really warm out. So those two can't really happen together, but we're not worried about that. P and Q. Therefore, it is really warm out. That's Q. P and Q, therefore Q. That one was, whoops, did I just zoom out? I didn't mean to do that. Let me zoom back in. That one was simplification. Here it is. P and Q, therefore P. Or Q and P, therefore Q. This is simplification. All right, example 3. Determine whether each argument is valid. P is the for loop is faulty. Q, the while loop is faulty. R, the hardware is unreliable. And S, the output is correct. Our argument is P implies R. P implies Q. Therefore, P implies R and Q. I'm going to start numbering. This is going to be 1. This is going to be 2. So for number 3, let's see. I want to know, I don't really know anything about any of the individual arguments. I don't know anything about P, Q, or R separately. And I don't think I can determine anything about any of those from what I have written here. And I don't really know anything about R and Q together either. And I can't use my transitive. This would have to be an R in order to do that. So I'm having trouble figuring out where to start. But one thing that I think I could do, and we haven't had to do this yet, is I can look at some cases. Both of these statements that I have in my argument depend upon P. So we can look at the case where P is true, and we can look at the case where P is false, or we can look at the case where not P is true. And then we can look at how does my argument fall, because P is either going to be true or not P is going to be true. So let's look at these two cases. Let's look, this is called a conditional proof, at two cases, P and P is true or not P is true. So let's do case 1. And for point number 3, I'm going to say that this is P. And I guess this is from case 1. So argument 4 is going to be, okay, well now if we're assuming that P is true, then we know that R is true. And that's from 1 and 3. And that's due to modus ponens. I also know, number 5, that Q is true. That's from 2 and 3. That's also modus ponens. Let's see, what can I say next? That's 3, 4, and 5. Well, if I know that R is true and Q is true, then in number 6, I can say that R and Q is true. Oops, I said R, but I wrote P. I can say that R and Q is true. That's from 4 and 5, and that is conjunction. And now I can say in my last step that P implies R and Q. This is true, and this is true. P is true from step 3, and R and Q is true from step 6. So this means that in case 1, I have a valid argument. So let's see if case 2 also yields a valid argument. In case 2, I'm assuming that not P. Then for step number 4, well, actually, I think this might be my last step, because if not P is true, then that means that P is false. So P implies R and Q is vacuously true, because P is false. So it doesn't really matter what R and Q is, because since the first part is false, the whole statement itself is true. So this case also leads to a valid argument, since both of these cases together represent the only two possible cases. Either P is true or not P is true. My entire argument is valid. You will see one like this on your homework where you have to look at multiple cases. I want to say it might be the very first one. So keep that in mind, that this is something that you can do in order to help solve your problems. Okay, I think we're ready to look at the last one. This is the last one in this section. B, R or S implies P. S implies Q. P or S, therefore R. All right, so I've got, I'm going to do another color. 1, 2, and 3. Let's take a look at this one. This is another one where I don't know anything about an individual element. I could try to assume something like I did in the last one, like 2 different cases, but I don't want to do anything with R because that's my conclusion. So I'm not allowed to assume anything about R because that's the conclusion. I could assume something about P, but that's not really going to help me because P's here and P's here. I could assume something about S. That'll help me figure out things about Q, but that's not going to help me figure out anything about R. So I'm having trouble coming up with a good strategy. So I'm thinking this one might be invalid. So let's look at the truth table. So I've got P, Q, R, and S. And then my hypotheses are R and S implies P. I've got S implies Q. I've got P and S, and then I have R again. So I want all of these to be true, and I want this one to be false. So let's maybe try to engineer that. So I want R to be false, but I want all of these to be true. And I want to see, is it possible to have this set up with some values over here. So if R is false, then R has to be false. So if R is false, I want P or S to be true. What if, so I might just have to try out a few things. What if S was true, then Q also has to be true, and P, let's say P is also true. So let's see. So now let's double check to make sure that what I wrote here is going to lead to this outcome over here on the right. R or S. R or S is true. Therefore, P, which is also true. So this is true. So this is true implies true, which is true. All right. S implies Q. True implies true, which is also true. Okay, that's good. P or S, they're both true. True or true is true, so that's right. But R is false. So here I found one instance where all of my hypotheses are true, but my conclusion is false. So this argument is invalid. And that is the end of this section. See you next time.